All right, good afternoon. Good afternoon. I guess I have to crank the volume up. Good afternoon, there we go. Okay, we're ready to jump into our next lecture on renewable versus non-renewable resources. I've got a few announcements before we get started. The first is that Vineet, the GSI, will be sending out an announcement on office hours, locations, and times. He's still finalizing classroom locations, but plan on Monday, Tuesday. The homework assignment will come out tonight. Again, you'll have a week to get that done, and so it'll be due Thursday at the start of class, and you'll submit that through C-Tools as identified in your syllabus. And then I also wanted to note that the Badgers are in first place in the Big Ten Conference, unranked, undefeated. They crushed Indiana, so I may have to eat crow in a few days. I understand that. Michigan plays tonight, but just a little reminder. Okay, we have a guest visitor. Sarah Schwimmer is from the Graham Institute, and she's going to give us a short talk about the good things that you can do in sustainability at the university. And so I'll pass the baton to her. You can pin that on, or you can hold it either way.
Okay, I'll just hold it. Hello. So I'm from the Graham Institute, and while I was an undergrad here, I was a Graham Sustainability Scholar. The program is a 2-year, 11-credit sustainability certificate program, and we're currently accepting applications for new scholars. How many of you are currently freshmen or sophomores? Okay, so this is relevant to you. It's actually also relevant for juniors who know that they will be here for a 5th year. So what this program is a sustainability leadership program for undergrads. And at the end of the program, how is it cutting out? Okay. It'll show up on your transcript and you'll receive a sustainability certificate. And throughout the program, you take 2 required seminars, both during the fall of your junior and your senior year. And you also take Environment 391, Sustainability in the Campus, which is a specialized project course in which students are able to work on sustainability projects that directly impact the university. And you also take 1 sustainability elective. And then everybody's favorite requirement of the program is that you have to do a field-based experience, and you're given $3,000 in funding for this experience. So far, scholars have gone all over the world. I was able to do a field experience in Detroit and in New Zealand. People have gone to China, Iceland, Uganda, just all over the globe right now. And you can either take an established field course or you can create your own independent study and you would still receive the funding. So applications are due January 25th, which is pretty soon. But it's only a 500-word personal statement, a resume, and your transcript, and you will be required to submit the names of people who will act as your references, but they have an extra 2 weeks to submit the references. So if you're interested in applying, don't worry, you're not going to be like rushing somebody to get a reference in within a week. You'll have time for them to do that. And we have a brief video from the Institute that we can show you. And while we're waiting, the program has some class components, but we also do a lot of programming outside of class that's really great, like a camping trip to Sleeping Bear Dunes in the fall for new scholars.
Volume could be an issue.
Okay. We could put the microphone by it.
I know. Yeah, the volume will work. Okay, we have a little technical issue.
It's fine.
What we will do is we will send out an announcement with a link to the video so you can watch that
Yeah.
at your leisure.
It's good. Okay, thanks for listening.
Okay, thank you. Well, we're ready to roll again. Okay, so we will, in this lecture, we're going to cover a number of topics in discussing renewable versus non-renewable resources. We will review the definitions of reserves versus resources, and then we'll talk about a couple of different models that we can use, pretty simple mathematical models to predict a production rate or a consumption rate of a given resource. And you'll see that we're going to look at both static and dynamic models, and they can bracket a fairly big range. But again, these will be pretty simple tools so you can get a feel for how long a reserve may exist. So what is a non-renewable resource? Well, renewable resources are those that can be replenished by the energy from the sun, nutrients from the earth, things like stone, wood, leather, bone. And then those can be replaced in time frames that are reasonable. So, renewable resources are things you're all fairly familiar with in a day-to-day use. Now, non-renewables are those that can't be regenerated during a normal life cycle of a product. They can be exhausted when consumption's rate exceed production. So, if you think about it, as little as 300 years ago, humans really subsisted off of renewables. They used stone and wood and bones and so on, but relatively few of those consumables were consumed. Even as we grew into use of iron and copper and zinc, the demand of those products was relatively low compared to the available resource. So if we look at this is an interesting graphic if you line up. It looks at kind of the shift of the use of non-renewables versus our dependence on non-renewable materials from renewable materials. So again, this is an interesting scale. We're talking about the Stone Age, the Copper and Bronze Age, and in this time frame, in the Stone Age, certainly we used rocks and carved out weapons and such, and as we moved into the Copper and Bronze Ages, those materials were used for implements and so on, and copper is kind of a soft metal, and that could be hardened to become bronze. But again, the big discovery was the use of iron. Wrought iron really displaced bronze as a metal, iron certainly can be melted with a blast furnace and manipulated, and it's a very hard metal to use. So, we're talking, then into we move into the 1800s or so and transition into the Industrial Revolution. The production of steel really transformed our industrial base, and through the Bessemer process and oxidizing impurities out of steel, out of iron, we could come up with a much more hardened material that could be used for a variety of processes. A big switch then, of course, came into the development of polymers, the use of plastics and so on, and we're now moving into a molecular age where you can, of course, use things like nanomaterials that provide a whole variety of uses that weren't even considered earlier. So, again, we started with renewables and we transitioned into non-renewables not because we ran out. We didn't run out of stones, we didn't run out of bones, but we were able to develop materials and modify those for a broader range of uses. To give you an idea of what the world production of some of these materials looks like, we're going to look at a variety of materials over world production rates, and I want you to keep in mind that this is a logarithmic scale. Now, oil and coal production is probably close to 9 billion tons a year, and it's quite significant. If we look at all the metals production, the vast majority is steel. Remember, this is a logarithmic scale, so we're talking about orders of magnitude greater production of steel than a lot of these other metal alloys. Polymer production is very significant. Again, we exceed really all the metal production other than steel. And moving into construction materials, ceramics, concrete, again, orders of magnitude greater than a lot of these other materials. So again, it's important to note that we're generally using about 10 billion tons of materials a year, which averages out to about 1.5 tons per person. Now that is on, again, a global scale. What do you think that would be in the US? Gut feel. 10 times, 100 times, 1,000 times? In the US, that number is going to be closer to 10 tons per person. So again, consumption in the US far outweighs its relative resource abilities, and we're using a vast share of the world's resources. So another way to look at this is on a pie chart instead of that logarithmic scale, and then of course you can see that concrete by far is one of the largest volume materials that we use, again, followed by metals, steel, and polymers. So one of the concepts we want to discuss today is reserves versus resources. And when we talk about mineral reserves, we're defining that as part of the known mineral deposit that can be extracted, of course, legally and economically. And again, that can change due to a number of different factors. So now our resource base is actually the real total that's there. It's going to be much larger than the actual reserve. Resources, the total resource box will include deposits that we're not aware of, we haven't found, we haven't explored. So an easy way to look at this is in a box type model. If you look at resource base being this entire box, that is, the resources are there in this fixed box, and this reserve box can grow or shrink depending on a number of issues. So our reserves are really what's accessible. This small box would identify what's been exploited. So what's already been mined and taken out. Our reserves are going to be limited by technology, by economics. It just may not make sense economically to extract certain minerals. But the total, again, is going to be, the reserves are going to be a subset of this total of the resource base. So again, this resource base is going to be fixed. The reserve box can move and change its shape depending on a lot of different factors. So again, if the economics are favorable, that box can get bigger. If the economics don't favor extraction, then this box will get smaller. Okay, any questions on the difference between a reserve and a resource? So again, the resource is fixed. It's there. Our reserve is the actual amount that is viable to extract. Now, of course, we'd like to come up with some models to predict how long a resource may be available. We've got a couple of different ways to do that. We can look at historical data and simply extrapolate out a rate. We can also come up with models, exponential growth models, to predict resource production or consumption. So a very simple model to look at is an exponential growth model. And here we've got production rate plotted versus time. And this relationship can be expressed as this function. dp dt is going to equal a resource a rate constant times the actual production rate. And so we're interested in the production, which will be equivalent to the area under this curve. And so we can write a very simple integral and solve that function to get an expression for the production as P naught, which would be our starting production, times e to the production rate constant times time. Now what we'd like to do is come up with a simple arithmetic way to solve for that rate, and so we can take the log of each side and solve essentially for to get a representative line, and the slope of this line, if we're plotting the log of the production rate versus time, the slope of this line is going to give us the production constant. So if you have, again, a series of data, you can plot the log of the production rate over time. The slope of the line will give us R. So it's a pretty straightforward expression. So how does this model compare to real data? Is it usable? And so we're looking at the production of three metals of aluminum, copper, and zinc over time, and this is from the 1900s out to nearly present times. And so these are actual production rates, and so you can see the aluminum rate, extraction rate does look like a typical exponential rate, and the copper and zinc rates are not quite as steep. The question is, can we come up with, use that simple model to come up with an extraction rate? So in this bottom graph, we've plotted the log of the production rate. This is a log scale versus time, and you can see we've got aluminum, copper, and zinc plotted, and slopes equivalent to about 10% per year for aluminum, 5% for copper, and 2% for zinc. One little anecdote. Anybody hear of Oberlin College? It's a couple hours away in Ohio. The chemist that figured out the process to make aluminum was at Oberlin College when he did this. He later formed the Alcoa Company. When he died, he left almost all of his money to Oberlin College, so that's why you can go to school there almost for free. So the next time you have a can of Coke or Bud Light, that aluminum can, the chemist who figured out that process came from Oberlin College. All right. So what we'd like to do is identify the time to produce or exhaust a resource. And we've got a very simple relationship that we can use. It's going to be our static index of exhaustion, where we simply take our existing reserves and divide by the production rate. So our reserves, for example, will be in tons. Our production rate will be in tons per year. And when we multiply that out, our units on top will be in years. And so it's, again, we're simply assuming that the current production rate is going to go out into the future, and so we will calculate the time for that reserve to be exhausted. If we're assuming an exponential rate, we again want to be able to calculate that time to exhaust our resource. So again, we solved this equation earlier and came up with the relationship for the production rate given a given rate coefficient. So what we solved for the area under the curve, we set up an integral and substituted our expression that we had for P, and we can come up with essentially a dynamic time to exhaustion, which includes, again, our production rate that's going to be generated at our given exponential rate, this dynamic time to exhaust Q at that given rate, and P naught is our initial production rate. So we essentially have two models to evaluate how long a reserve will last. We've got essentially historical data to come up with a linear relationship and say, okay, the rate's going to stay the same, and we'll exhaust our reserve at a given time, or we can assume an exponential model and come up with a different time to exhaust that reserve. Okay, so we'll run through an example problem to show you how those models can work. And so we've got a case where we're looking at the production of platinum, which is important in catalytic converters. And we know that the production of platinum has risen from 145 to 217 tons per year over the last 10 years. We've got a reserve estimate of about 71,000 tons. So the question is, what is our time to exhaust the platinum? Oh, okay, here we are. All right, so we talked again about two different kinds of methods. The first being a static method where T, the static constant, is going to be Q divided by P naught. So Q is the current reserve, and we're estimating that to be 71,000 tons. And P naught is our extraction rate, and the current rate, not the old rate. We know that the rate's gone from 145 to 217, but our current rate is 217 tons per year. And so, using that static assumption, our time to exhaust that reserve is 327 years. Very simple calculation. So, what if we look at the data and it looks like it's a logarithmic growth model? Remember, we looked at aluminum earlier, and that aluminum production line was sloping up, and it looks like we may want to use an exponential growth model. So, to do that, what we need, our first step is really to calculate R. And so we know from our original expression that P is equal to P naught e to the RT. All right, we want to solve for R, so we can move P naught to the other side. And then we can take the log of each side. And then solving for R, R will equal 1 over T times the log of P over P naught. Now, from our problem, we want to know, we know that we've got a value of a growth rate of change from 145 to 217 over 10 years. And so in this case, P, which is our production rate at the end of our time period, goes on top. And P naught in this case is 145 because that's at the end of our time period. And that's 0.040. So just so that you don't get confused, here P naught was our extraction rate at the start of our prediction. Here we're looking at the rate between P and P naught, and so P naught here is 145. So don't get locked into thinking P naught is always some number, but again, look at the problem and understand where in the production rate you're looking to do the calculation. Okay, so then we have an equation for our dynamic T. And that is going to be 1 over R times the log of RQ over P naught plus 1. So if we plug in the numbers, we again have an R of 0.04 times the log of 0.04. Q from our problem statement was 71,000. P naught, now here again, P naught is going to be the production rate at the start of our prediction, so it'll be 217 plus 1. And if we do the arithmetic, our T dynamic solution will be 66.1 years. So the take-home message here is that you've got this static production rate that's based on your existing consumption rate, and that came out to be 327 years, assuming an exponential production rate, which is going to be much more rapid. That exhaustion rate is reduced to 66.1 years. All right, any questions about the problem solving? The only thing you've got to watch out for is pay attention to what P naught is and where you're looking in terms of the prediction. Okay, any questions? All right, we'll move on. Okay, so now it's time to talk a little bit about money and price. There's a fairly straightforward way to look at the rate of discovery versus the rate of production. And if we are looking at a mineral, we can predict that essentially the rate of discovery of that material will follow this sort of curve to identify the reserves that are available. Now the production rate will follow a similar sort of pattern and curve, but it's going to be shifted off to the right because, of course, one has to identify the reserve, extract the material, find a use for it before it goes into production. So the price that will typically follow is that, of course, when the quantity of the material is low, the price is going to be pretty high. As the production rate increases, that price is going to drop. And as the reserve is depleted, then the price, of course, will go up. So this is all fairly simple, fairly straightforward sort of prediction of reserve versus production rate and how that's going to change versus time. Now, oil is a pretty interesting resource to take a look at. And here are actual data. The bar graphs represent past discovery of oil over time in billion barrels per year. And so we've put together kind of a smoothed out curve that describes the reserve discovery curve for oil. Now, there certainly was talk that sort of the peak oil value, the time that perhaps our production would have peaked, was going to be out in sort of this 2005 time frame. But that's changed a lot lately. And the price of oil has changed, of course, with the supply, and there are a lot of political and economic forces at play in the production of oil. Does anybody have an idea of what a barrel of oil goes for these days? I mean, we know how much it costs to fill up your tank. What's that? 85, yeah? High 80s, low 90s in that price range. That's pretty good. What was the price of oil back in 2008? We had speculators running wild. The price of oil was about $145 a barrel, so it was pretty ridiculous. and corresponding gasoline prices that followed. Well, now the U.S. produced more oil in this last year than it ever has. Imports from Saudi Arabia have dropped. Can anybody tell me the top 3 states for oil production in the U.S.? Alaska, Texas. Any guess on what that third one could be? North Dakota. That's right. And why is oil production gone crazy in North Dakota? Anybody know? Fracking, technology. So North Dakota actually now is the #2 producer of oil. It is ahead of Alaska now in terms of total oil production, driven by technology. So this production curve is not quite so predictable. We've got advances in technology that can open up reserves and can change the equation. So the price of oil now is down to, let's say, $84, $85 a barrel. So the question is, when does this curve drop off? When is the resource exhausted? I mean, that's highly speculative. There's thought that we hit our peak oil production back in 2006. Now it looks like it's going to be stretched out to 2020. We've got movement to using renewables and other forms of energy. So trying to predict the future of oil production prices and its production rate are pretty challenging. So that's one example. Again, you've got multiple factors in play. Technology improvements change the reserve. Political and cost pressures change the reserve as well. All right, we have another model available to us to predict production. This is a little more reasonable, this sort of Gaussian curve that is again more reasonable than a typical exponential curve. We saw that the numbers can be really quite drastically different between existing production rates and using an exponential model for predicting how long a reserve will last. So the Gaussian model is a little more accurate than some of those other models, and we can again predict a time to reach our given maximum production rate using this relationship. So we've identified a number of variables to characterize. The first is the existing production rate of the resource. The second is the maximum production rate. T sub m, the time at which the maximum production rate occurs, and sigma, the standard deviation, the measure of the width of this bell curve. So we can solve an equation for P and drill that down into T sub m expressed as a function of the standard deviation and the maximum and given production rates to reach that number. So the Gaussian expression is a pretty valuable expression to have. Now we can, if we can come up with a reasonable guesstimate of the total amount of the resource that will ever be produced, we can start calculating some of these maximum production rates. So let's move on to another example. We have a case where the total production rate of coal is going to be double the 95 recoverable reserves, and we have an estimate of that is 268 times 10 to the 9th tons. Now we've got a production rate in 95 given as 1 times 10 to the 9th tons per year. So the question is, how long is it going to take us to hit that peak production rate that's going to be equal to 4 times the 95 rate if we follow that Gaussian production curve? So as a reminder, we've got a couple of expressions. We've got this maximum time to hit that peak production rate, and we've got an expression for our ultimate reserve amount. So we are, again, assuming, given the problem statement, that we are going to be looking at 2 times the reserve rate, or the reserve, so 2 times 268 times 10 to the 9th tons. We have a P naught of 1 times 10 to the 9th tons, our production rate in 95. And our P sub m is, again, from the problem statement, 4 times that production rate. So again, the values that we need all come out of the problem statement. Our ultimate reserve, we're going to say, is 2 times the 95 reserve. We have our 95 production rate, and we want to know how long is it going to take us to get to 4 times that production rate. Okay, so step 1 is to calculate the standard deviation of that curve. And so it's, again, a matter of plugging in the ultimate reserve amount, which we said was 2 times the 95 reserve. P sub m, our ultimate production rate here, we said was going to be 4 times the current rate. And so we plug in the values and we can calculate out our standard deviation is 53.5 years. To get back and calculate T sub m, we go back to this expression. Again, we've solved for the standard deviation, so we plug that in. The ratio of P sub m to P sub naught out of our problem statement was 4, so we can calculate that out to be 89.1 years. So essentially that means within 89.1 years we're going to essentially hit a peak production rate that's going to be equal to 4 times the 95 rate. So you'll have opportunities to solve these sorts of problems in your homework. You'll be looking at exponential models, Gaussian models, and looking at times to hit certain production rates. So the Gaussian production curve, this is essentially this problem solved, but we've looking at this ratio both 2, 4, and 8 times the current production rate in 95. So you can see that the shape of that curve is highly dependent on what we think that ratio is going to be, and the standard deviation associated with that. So these estimates, again, are going to be highly sensitive to that ratio of P sub m to P sub naught to give us an idea of how long that reserve is going to last. And again, you can come up with some wildly divergent time frames depending on what kind of assumptions go into that production rate. Okay, any questions? Okay, so we're going to wrap things up today. Just in summary, we identified renewable versus non-renewable resources. Our non-renewables were the things that we can easily grow or raise or manipulate, stone, wood, bone, and so on. Our non-renewables, of course, are minerals and such that we can't recover again. We looked at the resource reserves versus the resource base. Remember that resource base was the fixed box, our total estimate of the amount of material that's there, and our reserve can fluctuate based on the technology that's available, regulatory drivers, and price drivers. So at the end of the day, the reserve is what can be extracted, but that number can change depending on things like advances in technology like fracking. Okay, we looked at a couple of different models of resource production. That exponential model can give you some pretty high numbers. Again, it's going to be very sensitive to what we expect that exponential growth rate to be. The Gaussian model can give us a little better predictor, but again, it's going to be sensitive to that standard deviation, and which comes out of the production rate that we use to calculate it. So again, understand the value of static and dynamic estimations of time. It gives you a pretty good bracketing, looking at historical production rates versus some predicted model rates. Okay, any other questions? We've got, we do have time. We've kind of gauging the material that we're presenting. Vineet, do you have any other information regarding homework assignments or office hours? So again, the assignment you'll find the problems to be similar. Well, just settle down. You got plenty of time. The assignment will be similar to the problems we've solved in class. If you have any questions, email those to Vineet or myself. If it's too hard for me to answer, I'll just send it to Vineet and he'll take care of it. So your better guess is to go to him. Michigan basketball tonight. NFL football this weekend. First week of school in, so it's Thursday night. Things are itching. So anyway, have a good weekend. Talk to you on Tuesday.